All right, well, everybody, thanks for coming and giving us your time this afternoon, this morning, wherever it is that you reside. My name's Sam Scher, and I'm the host of Geochemistry and the principal consultant at LKI Consulting, where I work with a lot of horrific geochemical data. Um, but I'm always, I feel, in pursuit of how to deal with legacy data in an easier way, which has led to a ton of a ton of discussions, particularly with Putra. And that was part of our inspiration to start this webinar for you guys today. So Putra, if you want to introduce yourself.
Absolutely. Hi, everyone, and thanks, Sam, for inviting me to present at this webinar. My name is Putra Sadikan. I'm the product manager for the ioGAS software by IMDEX. I'm a geochemist by background. Got quite a few experience looking at horrific data set, same as every geochemist out there. So the way that we're going to talk about it sort of from my end today is just showing you some examples of what poor data looks like and what are some of the things that you need to look out for. But there's more of that in the next hour or so. But that's it for me.
Definitely. So yeah, like Putra said, we have a combination of some slides to give you background for the demos that he's going to do, which I think definitely is the best way to see it and to learn it and to try and hopefully start some discussion around it. If we don't have enough time at the end, just leave all your questions either in this chat or you can submit them to me or Putra, and we'll respond to you. And let's see. Yeah, that's it. I think we're ready to go. So Putra, if you want to hit the first slide. Yeah, so what's historic geochem data? Basically, historic, legacy, I think they're often used interchangeably, but this kind of data will be sourced from either reports, from databases that you get because you've acquired new companies or bought them. You can get them from maps too, but basically they're just decades of data from historic exploration or mining programs. They're varied in quality. That quality is either because you did a non-appropriate analysis for the type of material that you had, or it's just because the data is from 50 years ago. So it's really going to depend on analytical methods and the standards used at the time, which we're going to talk about today. But it's still important because you can still get insights from this old data. It can still potentially help you identify anomalies or trends that might not be obvious in the current landscape that you have, because maybe you've started mining and those samples are no longer able to be resampled, for instance. It'll help provide baseline for these geochemical landscapes. And if you're able to effectively repurpose this data, it can lower the cost of potentially having to do new field programs. So it can help support too strategic modeling and interpretation when integrated with these newer modern data sets. So yeah, they're definitely important. Next. But it comes with challenges because you'll have data gaps, particularly a lot of times you'll have gaps in where you don't have metadata. All metadata is it's all that contextual information attached to the actual assay. So whether it is rock type or it is telling you something about the analytical method, it's really important. The more metadata that you can have in your data sets to begin with, the easier it will be for future you when trying to do a geochem interpretation. But yeah, going back through it is always going to be tricky. Okay, go ahead. Yeah, so the first thing we're going to talk about is analytical considerations. Here we're going to chat quickly about digest, instrumentation, and detection limits. So digest type. I'm just going to focus on aqua versus acid because at a high level, that's usually the biggest things that we see in these legacy data sets. Where that becomes difficult to use is oftentimes you'll use an aqua on, say, rock core data, and it's not going to be able to dissolve much more than sulfides. And in this diagram that we have to the right on this slide, you can kind of see where these different leaches will be able to get up to and digest a certain type of mineral in your sample. So a lot of times us using this agarija data, it's not going to be helpful for us looking at alteration or lithologies in our data sets. Next. This is a really great graphic, and this is just showing you elements that will or will not be affected with agarija or 4-acid in silicates and sedimentary rocks, as well as carbonates. And basically, it just goes to show that especially in some of these elements where we're going to be using them to understand our alteration or lithology, it becomes really difficult because there's a really big difference in what we're going to be able to see in our data sets because it just won't be able to dissolve as much of those minerals and get those elements into solution. Next. A really great graphic here as well. So here we're looking at a diagram that's plotting zirconium versus titanium, just having a quick look to see if we can differentiate andesites, dacites, rhyolites, and basalts. And in that blue down there, you might say, oh my God, this is so exciting. I have like another potential new lithology over here. You might want to highlight it in ioGAS, but really, if you just go on and put on your metadata, you'll see that really the only difference between the purples and the blue is that everything in blue is agarija because you just can't dissolve zirconium really at all. Better yet still than this is because zirconium is hosted in a highly resistant mineral. We'll be using a fusion style digest. So just always think about what kind of rock you're trying or mineral you're trying to get out, and that will help guide your decision in what kind of digest to use. Next. A lot of times we focus, am I doing a 4-acid and agarija? And we kind of will just gloss over and say, oh yeah, I'll just do an ICP. The fact of the matter is that there's differences whether you're talking about ICP MS or OES, AES, and it just has to do with detection limits. So if you're at a mine site, you don't really care about getting super low trace element data because you're in the heart of the system and it's not relevant to your program. Sure, go for the cheaper option and go for an OES or an AES finish. It's still going to produce great data, but if you're in the exploration environment, you're going to need ICP-MS data. Likewise, using an XRF. XRF is really effective for major and some of the minor elements. A lot of times you do a whole rock style analysis, they'll be combining XRF and ICP with it. But it offers really high precision. So that could be the best for what you want to do in your study. So again, it just depends on what sample that you have, but using the wrong finish can really affect the kind of data that you have to analyze later. Next. Detection limits as well. Just one last thing to just kind of highlight this. In the light gray, that is average crystal abundance for the elements on the x-axis. Below that, in the darker gray, what's highlighted is kind of the detection limit that you'll need of your instrumentation in order to say, okay, great, I can be able to detect my nickel, detect my zircon, et cetera. Really what you'll see here for many of these elements, if you don't have that green curve over there, the green is ICP-MS. If you're not using that, then you probably won't even really be able to detect it in a way that's meaningful for your data. You can, to an extent, for some of the elements, but again, just know what you're looking for, and that's going to guide what type of finish that you're going to need. Next. And here's just something that just shows it to you kind of in a very ioGAS style way and very black and white. And that is that these are 4 different analytical methods that were used in this data set. And what we're looking at here in purple, blue, those are detection limits that were quite high or quite low, rather, at 0.1 and at 1 ppm. And then above that, you see in the black and the gray how we're missing a lot of data in there and we can't really see anything. And that's just because the detection limits were so high. But the average crystal abundance of bismuth is 0.17 ppm in that dashed line. So again, bismuth is a great pathfinder element for gold in this system. And if you're unable to get your bismuth in a way that matters, then why are you even bothering analyzing your sample? Next. Quick QA/QC stuff right here. I'm just talking about strategy, and then Putra's going to demo some stuff. So go ahead. Yeah, so things to look at and what Putra's going to be like just kind of really pushing in when he does this demo is that with exploratory data analysis, when you're looking at your geochem data, there's going to be a few problems that are going to always really pop up and you'll just see again and again, which is what we're going to see really over the next 3 demos with Putra, which is that we could have less than detection data, we can have overrange data, the opposite problem. We have problems with data that's not normal. We can have missing values. We'll have combined groups of data that have inconsistent digest, instrument finish, analytical stuff that we just have to really pull apart and be really critical of. And also geochemical data is spatial. It's not just chemistry. So if you have the wrong coordinates in there, the wrong coordinate system, that's really gonna affect this. Next. What we're gonna do today, one of the ways that's probably one of the more preferred ways to deal with detection limit data is to replace it with a fixed proportion, usually half. You're also going to have to deal with in your data sets. A lot of times there's going to be more than one detection limit. So it's just something to keep track of and to really understand what's going on with your data. And then also, if you're going to be doing anything more than univariate or bivariate analysis, you just have to keep in mind what is the percentage that you are going to be replacing. If it's more than 30 some odd percent of your data, then you probably shouldn't use that element going forward in a multivariate analysis because it's just not meaningful at that point, and you're going to be losing a lot of samples. Next. Yeah, this is a great slide too. I think the ones I just really want to highlight, null data, keep it null. Don't replace it with zeros. That's a nightmare. Keep your units consistent. And particularly if you're going through and then all of a sudden you have 10,000% iron, you probably have mixed units in that column. So units are super important. And just don't forget about that when you're going through these legacy data sets. It is just like landmines everywhere. Go ahead. Last thing that we're not going to talk about here, but is a thing that you can do. It's more common when people that start to do like machine learning, data science stuff, but you've probably heard of people talk about imputation, and it's a way to treat stuff that's below detection limit. And the only thing, I think I'll say 2 things. If you want to do this kind of stuff, you definitely have to use Python R. There's a package called Z compositions in R where you can do this. But just pay attention. If it's starting to impute data that doesn't make sense because your detection limit is maybe particularly high, and then it's putting in values that look like too high for like what you think it really should be, then just probably say no. You have to be really critical while imputing data. So don't just use it as just like, okay, I'm going to use this package, throw it in, and then it will give me an answer that will be usable. You still have to be really critical of that data. Okay, next. All right, so now everything that I just said in the past 14 minutes, Pooch is going to put into a demo for us.
Excellent. Thanks, Sam. Just want to add something to your last slide. I think it comes down to common sense. If you want to do things like below detection limit replacement and imputation, whatever the number is, look at your rocks and see if it makes sense. If you compare it, especially to your mineralogy and things like that. So always know what's a reasonable number to look at in your data, and go forward with that. All right, so let's jump straight into the demo. So we're going to be using the Flin-Flon dataset for this demonstration. I'm not going to talk too much about the Flin-Flon data, but it's a dataset that I used for my last webinar on the subject. And essentially what it is, it's a public domain data. And if you want to try to use some of the things that we talk about in our webinar today, you can go through this webinar recording, which I think will be made available, and then just have a go at it later on. All right, so this data set is a good example of what we need to look out for when we're looking at a legacy data set. So being a public domain data set, there's a few things that we need to think about and look out for, when we do those things for the first time. So when we look at this file, just straight off the bat, when we import it, a lot of the things that stands out straight away is that the column names doesn't have any units in them. And that's something that can be quite challenging, especially if you haven't seen a data for the first time, right? So in this instance, we don't actually have a unit next to each element. So luckily what ioGAS can do is you can guess the aliases. If you click on this button, it will just put in the right unit. But it's always a good practice to go through each one. So you can hover your mouse over each of these element name and try to see if the recommended alias kind of makes sense. But if it doesn't, then you'll need to fix it later on. And you can always remember that you can always come back to this window in order to fix up your units. So things like that. Right, so we'll just go ahead and go with what ioGAS recommends in this instance. And always remember to map your metadata columns. Just coming back to Sam's earlier point, metadata columns are not just information that has to do with the assay method, assay lab, or where your data comes from, what sample batch it is, that sort of thing. But it also has to do with the other information that relates to the geology. So even things like spatial information, where the samples are formed in your map space, and also what it is in relation to other samples that you have within your project. So other important meta identifiers include geology, logging, alteration, but also spatial information. All right, so let's just bring that in. And what we're going to do now is we're just going to quickly show what all of these data looks like in ioGAS, right? So if we're going to, the first thing that I like to do in ioGAS is, some people just go straight to the data doctor and just deal with it that way. But I find it easier to just go straight to something like a probability plot, which admittedly kind of looks ugly if you have a small screen like this. So I would recommend if you're using it on your computer to have a larger screen to do this part of the workflow. But in here, you can kind of see a lot of the problems that just pops up straight away. You can see that there's a bunch of values with a value of -2000. And if you look at it closely, there's a bunch of values that's reading at -17. So those are not actually real detection limit. Those are probably codes for something, either missing sample or sample not received, things like that, or they're code for something else. Either way, they are not detection limit. And the way to confirm that is to do something like a data doctor, right, afterwards. But we'll get to that in a minute. One thing that I would like to highlight from just doing it like this is you can quickly see if you have multiple elements of the same name but different units, right? So I got titanium in oxide here, and then I got titanium in elemental percent. So this is something that you see in a public domain data set, especially if it has been analyzed using, say, whole rock XRF, but also a multi-acid sort of digest. So something like a 4-acid digest will be reported as elemental percent, and from XRF will be reported as something like a oxide percent. So this is a good example of why you would need to look out for this sort of thing. Okay, so, and there's also another example here. I think it's chromium somewhere in here. All right, so a good way to quickly test for that, I know it's a bit hard to look at a probability plot this huge, but a quick way to do it is actually going to the select variables dialog, and you can press the right mouse button in here to sort things alphabetically, right? If you press your right mouse button once, you can sort things alphabetically and you can see elements of the same name, but different units and an oxide elemental combination. So you can see that chromium that I was talking about just now, and you can see that titanium duplicate in here. So you got one in oxide, one in elemental percent. So things like that. All right, so let's just jump straight into the data doctor. And the data doctor, as the name suggests, it just lets you look at your data and see sort of the issues that you may see in your data itself. So what I mentioned earlier, we have a bunch of rows at -2000 and -17. It's not that many, right? And I think there's a common pattern in here. So you will always have 1 -2000 and 3 at -17 for every element. So it looks like they are code for something, which means that you'll need to replace them with something else. All right, so what I tend to do, instead of going through the data doctor one at a time, which can be quite tedious, there's a button in here called the Find and Replace tool, right? So that's in the data ribbon, and you want to run it on your selected columns only. Okay, so what I want to do is I want to replace the ones that have minus 2000, and I want to make sure that it matches whole cell. And to replace, you want to make sure that it matches whole cell because you don't want to replace your sample ID metadata column with with the number minus 2000 in it, because there are some that has this characters. All right, so I'm just going to do that. And then I'm going to replace the ones that has minus 17. So I've done this before, right? So all my recent replacement lists are here. Okay, so I'm just going to do minus 17. And let's just go with that. I think there's minus 227, but we'll just deal with that manually in the data doctor. So one thing not a lot of people know with ioGAS these days is that we actually now have the ability to edit your data window by clicking on this button on the right-hand side toolbar to toggle edit mode. So you can click on this button to double click on each cell and just modify them yourself. But there's a red box around the data window just to show you to be careful, because the change is permanent and we actually log it in a change log in the file. Okay, so this is another key message I want to make across in this webinar, is that when someone sends you an ioGAS file, always make sure that you look at the change log, because it shows that if someone has done any replacement, below detection limit replacement, things like that, it will show up in the change log. And if someone sends you, if your database person sends you a file that already has the below detection limit value replaced with a positive value, you should have a conversation and ask what the original value was, because there's nothing worse than replacing your below detection limit value with a real value without knowing what the original detection limit was, because that can be quite dangerous, because you don't know what you don't know in that sense. Okay, so let's go back to the data doctor. And what we're going to do now is just what I like to do in this sort of data set is that we have multiple detection limit for each element. So what I'm going to do is I'm just going to click on, so there's two ways of doing it. I can choose the lowest negative value, which is 0.1, and pick half of that value as the replacement. That's what most people sort of recommend, but in this data set, I recommend, because we have different methods or different labs for each of the detection limit in here, I would try to say use a different replacement for each of those detection limit, but it sort of depends on your appetite and what you want to do. So in order to apply a unique replacement to each detection limit, I click on this button, suggest row by row. And you want to be careful with this, because some of the elements here, like bismuth, there's a code for minus 227. That is not a detection limit. That is a code. So I'm just going to replace that with null values. And let me just scroll down quickly. So there's a minus 999. So that's a classic. I'm just going to put that as a null. There's a minus 3.2, but this is LOI value, so it is a bit tricky to deal with this sort of thing. But let's just leave it as is. Let me just scroll down quickly just to see if there's any other code that we need to look out for. I think it should be fine. All right, so we click on replace all in here and we click apply. And remember that when you click on your change log, it will show you exactly what you've done in the file. So that's it. All right, so we've done the data doctor step, and let me speed up just to for us to move to the next bit. What we're going to do now is we're going to look at your probability plot again, like this. So this is what it looks like now. So it looks a bit better, but we still see some funny things in here, right? So this is another funny thing, all right? So notice this sodium, there's Na2O ppm. There's a large value in here at the top, a value of 235. So something's wrong with this column. So let's look at this, and look. Some of you may already be guessing what's wrong with this, and it's because we alias it as a different unit first of all, and there's an outlier here that we need to take care of. So we can probably replace this with something else, but let's look at that later. All right, so what we're going to do now is we're going to go back to the column properties dialog, and we're going to re-alias Na2O as %. So that's the first thing we're going to do. So every major oxides in here, we are going to be aliasing it as weight %. So that's the first thing we'll do. And the second thing we'll do is we're going to just select Na2O, and we're going to do a search and replace. So what is that value there? So I think that's a 235. So what we're going to do is we're going to replace 235 with null. So if you want to replace things with null value, just leave it as empty in here. And that's it. It's just going to replace one occurrence with null value. All right. So nice and happy. I always make it a habit to save my ioGAS file, to save a session as an ioGAS file, just so I can go back to it again. And one last thing that I'm going to show in this demo is looking at the effect of having different analytical methods in the file and what that looks like in your data. So those are some of the things that you can't easily see just looking at the probability plot by itself. I mean, you can sort of guess based on the distribution in the prop plot, but also in the histogram. If you plot up your histogram like this, you can kind of tell if there are multiple methods, but always not all the time, especially if they're closely or they're somewhat similar to each other. So what I would like to do is try to see if you have the appropriate meta columns for that sort of thing. So if you look in your select variables dialog, you see there's a few columns in here that corresponds to analytical method, source file, lab, and batch. So what I'm going to do is let's see what that looks like in a split probability plot. So I'm going to open a split probability plot. And then what I'm going to do is go to the attribute manager and auto attribute by my method column. And you see how it splits the data into multiple populations, and some elements were only analyzed using one method. Okay, so for example, things like there's a good example in here. I think it was sulfur in here, and chlorine was only analyzed by ICP. And I think same as some other elements in here as well that you can clearly see, right? So this is a good way to check, especially if you have the data, to show that there are multiple populations, within the data itself, based on the different sample method. And there are some that are quite different, but some that are quite similar. So if we pick I think a good one to show was probably scandium in here, where it's well, it looks a bit different. So if you look at scandium in here, ICP and the XRF methods, both of those populations are clearly quite different, that you can see from here. And something like I think I was looking at antimony in here as well. So it's quite drastic, where you have two different detection limits in here for XRF. And then as a whole, you have a higher detection limit for XRF. But in the upper range, if you do get some values, you get a bit of a better precision. But ICP, as you know, would have a lower detection limit for some elements. So things like that, right? So if you have the metadata, yeah, you might as well use it. All right, so let's look at what this looks like in 3D space. So what most people don't know is that in ioGAS, if your data is already desurveyed, so if you already have a 3D coordinates, we actually have a thing called attribute map 3D, and you can visualize things in, it's a pseudo 3D viewer, and I call it a pseudo 3D viewer because it doesn't have coordinates on the axis, but it's good enough to show you the distribution of data in 3D space. You cannot bring any surfaces or things like that, but this is, I would argue that this is actually the most important thing that you can do if you have a drilling program, because it allows you to see the relative location of your drill holes next to each other. Not so much the coordinates, but just making sure that your holes are sort of in the right place. And if your spatial patterns to your geochemical interp are pointing at the right direction, or if they're trending towards something that you'd be interested in. All right, so one thing that I would like to highlight from here is that we have a good overlap between the two methods, which means that it's not like one method is representing one part of the geology and the other method is representing the other part of the geology. So that's not what we're seeing here. But what, again, one thing to highlight is that we actually have a mix of surface samples and drilling samples as well. So if I look at, there's a column here called sample type. So we got a bunch of outcrop samples and we got a bunch of drilling samples, right? So different colors that you see in here. And what we can see is that a lot of the surface samples, let me go back to, just gonna click on the undo button, actually. So not many people know this tool as well. But if you undo and redo, you can go back to between states of the attribute manager, which is quite cool. So if we look at the colors that we see here is ICP and XRF, a lot of the surface outcrop samples were analyzed using XRF instead of ICP. So if you're looking at a comparative study of your drilling and outcrop samples, just be wary of that, that some an analytical method is constrained mostly to a certain sample type. So that's something to keep in mind. So it's always a good check by doing it like this. One last thing, let's bring up a Hallberg diagram, a classic Hallberg diagram when you plot titanium and zirconium on the X and Y axis. And what we can see from here is that the values are quite low. And even though we're analyzing it by ICP and XRF, based on such low values in here, it can indicate either two things, either because we're using a certain digest like Aquaregia, which doesn't produce that much of a high value because you're not dissolving a lot of the resistant minerals, or we're looking at a high level of alteration, which in this instance, we do see a lot of chloride alteration in here, which may push some of these numbers down. But always try to understand why we see low and high numbers in some of these diagrams. Don't take the boundaries of these diagrams too hard. You just have to kind of understand what the numbers really mean. So always, even though the ratios are important and the ratios are what determines which plots in which polygon, always think about it in the context of why are my values so low? What can explain that in that sense? All right, over back to you, Sam.
Okay.
Let me just make sure I get the right slides. There you go. All right.
Okay, cool. Let's talk
So
about.
So we've done this step, right?
Yes.
Yep. Okay, good.
Very cool. So fixing data sets. So questions to ask, what problems are in your data set are you inheriting? Can they be fixed? We'll talk about data leveling, residuals, and we already chatted about imputation. So, okay, let's go. Okay, so when we're talking about data leveling, and that's all that is to say is just pretty much just gonna, if we have, just for simplicity, we have two different analytical methods, and can we take those numbers and make them so that they more or less normalize to each other? We have to think of first, what are we going to level to? We can think about, do we want to do it to geology? Do we want to level to analytical methods, sample type? We just have to be cognizant of what we're going to be doing. Next. There's a lot of options in ioGAS as to which way you can go about leveling your data, methodology to use. We're probably going to use, I would think, either a log z-score or a robust z-score, but these are just all the different options that are available to you with some descriptions. Next. So in this example, basically what we're looking at here is we're looking at two different analytical methods. The red one's not great, but just for this example's sake, we're just going to move forward with it. So basically what we have is we have cobalt at these two different concentrations, if you will. How do we make these data sets talk to each other? And the whole idea with leveling is that we're going to take these and just make them meet more or less in the middle. Okay. So this is what this looks like. So we have ICP in red, and this is on the map, and we have XRF in the green on the left. So you can see the way in which these were analyzed. So maybe two different field campaigns. But basically on the right-hand side, you can see the cobalt actual raw data here. And the question when you're looking at this, maybe you're seeing it in a map, you're like, oh, there's no kind of anomalies up in the upper right-hand corner, so it's not even worth like going to explore there. But if you're also looking between the different metadata that you have, you might then notice, oh, actually, it's two different analytical methods. So next. So on the left is something that is raw versus once you've leveled it, that's what your new anomaly map can look like. Next. Okay, so now Pooja's going to take you through that.
Oops, sorry, I was on mute. Okay, so when we have sort of an example like this, and this is actually quite a perfect example because we only have two methods to deal with. So as we can see from here, let's pick an example, right? So let's pick an example of an element that has quite a different population due to the different detection limits. So let's pick something like, I think I was looking at, antimony wasn't a particularly good example, but let's pick, for example's sake, let's pick something like scandium, right? So if you plot something like scandium, and we see what that looks like in a, we already look at that in a probability plot, but let's look at it in a box plot, for example, like this. So you obviously have different mean value between the two populations, between ICP and XRF. And then if you want to plot that up in a map grid, okay, and if you plot an overlay of your attributes, you can kind of see that you have a bit of a population sort of bias, when you have a different analytical method. And the way that we're going to do this now is we're going to level the data. And we're going to pick quite a simple example where let's just look at, if we look at just one sample type. So if we look at just outcrop samples, for example, just keeping it simple. Sorry, so just pick it simple in our instance. So just look at the outcrop samples. And if we color it up based on sample method, this is what we see. So what we're going to do now is we're going to see that, okay, so you have some outcrop samples for scandium analyzed using ICP, some analyzed using XRF. So we're going to level this data. So leveling is done based on selecting that variable first in the select variables dialog, and you go to analysis and you click on level columns. All right, so two requirements. One is that you will need to have a metadata column that corresponds to the thing that you want to level to. So that's how it works in ioGAS. And you want to level by that particular column by selecting it in here. And then there are different leveling methods, which Sam has shown in that presentation slide. So in this instance, we know that scandium is, let me just plot up a log transform. And if we look at the probability plot for that element, this is another thing to highlight, is that the transformation that you choose in the leveling method depends on the distribution of your data. So if your data is not normally distributed, you want to apply, this is a histogram of scandium, you want to apply the right transformation to apply in here. Okay, so in this instance, I would use something which has a log10 transform, definitely not mean, because if you choose the mean value, the group mean value will be biased because of the distribution. Sometimes you can use median, especially if you have lots of outliers, but for non-normal distribution, sometimes it works. Gauss distribution can also work, and robust z-score. But for simplicity's sake, let's pick something like a mean log10, right? So let's look at that, or z-score log10 also works. But let's look at mean log10 transform, and let's compare that data now that we have that plotted up. So let's select scandium and the leveled scandium, and let's look at that in the prop plot. So that's exactly what that looks like, right? So if you look at the leveled data, you can see that the mean, which is that dot right there, it's sitting at the value of 1. And then if we plot the leveled column, look at that in the map grid, that's what that looks like instead. So you can see that the result is quite different, right? And it highlights, what does this highlight, right? So what this actually highlights is the anomalies within each, probably scandium wasn't the best example, but just showing you an example that's quite visual in here. But if you imagine looking at this using some of your Pathfinder elements, it can make a difference between knowing what constitutes as a signal to each method, as opposed to something that you pick up as an anomaly, whereas it's picked up as a background in other method or sample medium, things like that. So it allows you to level out, as the name suggests, it allows you to level out the variation and picks up sort of a broader anomaly sort of assessment across different things that are not necessarily related to the geology. And that's the sort of the power of leveling. And you can see that the distribution here is quite different. All right, so that's pretty much it. Over to you, Sam.
Okay. The next one is a favorite of mine. If anybody's ever seen me talk or get frustrated by something, it's how even in a geochem conference, we've seemed to have forgotten that metal scavenging and absorption of ions onto iron, manganese, aluminum hydroxides is a thing. I won't get deep into the mechanisms of this because that will take forever, but just take my word for it. Like, this is a big deal, especially if you're working in deserts. That's it. Like, it's a huge problem. Next. So for this, I think it's important first that we think about fit for purpose digest types. So if we kind of recall back to when we were talking about digest, if we go for a digest that is only digesting up until this particular species, then it will take away much more of that kind of additional residual effects of the scavenging. So you'll see like less I guess, drama out of the whole thing. So yeah, understanding your geological and your geochemical environment is super important when selecting an analytical package. And talk to your lab if you need guidance with this. Just know what you're doing before you do it, is always the recommendation. Next. So for instance, let's say that we're in a train where potentially you can have some of this metal scavenging happening. One of the things that you always have to be asking yourself is like, is this anomaly real? I think we're always asking ourselves that question anyway. But this one's just an important one. So what is it telling us? So looking at this arsenic here, we might be thinking, okay, here is our arsenic anomaly map distribution. Okay, let's go using this as a pathfinder. Let's go find the gold. Next. Oh, I decided to stop there because Putra's going to do a great demo of it. But like the whole point while Putra's doing this is just to be thinking, is this anomaly real based on the environment that I'm in? And I think like shockingly, you'll see that probably a lot of a lot of times when you see people present their geochemistry, they're like, oh my God, there's a real relationship between iron and zinc and copper and blah, blah. And they're just like, no, look, it's not real. So anyway, continue, Putra. I could go off on this.
Yeah. So thanks, Sam. So this is the ioGAS demonstration data set, actually. So you can access it from within ioGAS and have a go at it yourself if you want. So it's based on a public domain data set, right? So it's from a bunch of regolith samples in Western Australia. After this call, if you ask me, I can tell you where it is. What we're looking at here is if we plot, I'm just going to show that in a demo, what Sam showed in the slide. But if you plot a map of arsenic, and you can do two things with it. So you can plot it either as a variable map, or you can plot it as a map grid, same thing. All right, so what we're looking at here is a combination of two things, right? So we got the variable map, which just looks at the distribution of arsenic, right? You see, okay, so that's where your anomalies are, and this is where we should be focusing our effort. In this instance, there is an effect of scavenging that you might want to take into account when you start to look at some of these sample types, especially with a certain digest, like something like Equiregia, perhaps, that can digest more things that you might be interested in. What that means is that due to the absorption effect, we're looking at elements like arsenic that gets picked up by other oxides. And when you plot arsenic against iron in this instance. So if I plot it up like this, you see that there's strong positive correlation between iron and arsenic, right? So this is something that we see all the time. What does this mean? It means that there's a strong positive correlation, which means that a function of how arsenic is represented in the data is a function of how iron increases, right? And that kind of makes sense when we look at this. But what it also tells us is that a lot of that associated arsenic, when you digest the hydroxides that host this element, it means that when you take into account the effect of scavenging, what are some of the things that you can pick out once you remove the scavenging effect? There's two ways to deal with this. One is by dividing arsenic over iron. So that's one thing that sometimes I recommend for a quick and dirty way of looking at it. But you can also, so that's just a simple arsenic over iron sort of ratio, so normalizing it against iron, so to say. But a more mathematical and correct approach, I would say, is by plotting up a regression line, right? So if I plot up a regression line for my data like this, you can kind of see what I'm dealing with, right? So we're going to pick the residuals to the regression line. In ioGAS, we have a tool called regression in here. So because the data is not normally distributed, we have to apply a log10 transform. And what we see in here is the residual plot, right? And what we're going to do is we're going to auto attribute the outliers. So you see this triangle that I highlighted in here, those are the residuals to the main trend. Okay, so those are what I consider as the real outliers. So high arsenic, that it's independent to the trend that's represented through the regression. And I can use this information for a lot of things. When we look back to our variable maps, for instance, or our attribute map, and if I want to do is save this group as a new color, for instance, and then what I'm going to do now is I'm going to auto attribute based on that. I'm going to do the same thing with the size. Going to make it obnoxiously huge, and I'm gonna plot. What I'm gonna plot a. Not many people know this, but you can plot a raster map underneath this. So I can plot a geology map underneath my attribute map just to see how it relates to how really it relates to your distribution of real outliers and arsenic in this instance. And this is a much better one actually. So you can see where the anomalies are sort of sitting. And if I just highlight the fact that I just want to highlight the upper outliers, I can go back to this dialog and just making sure I select the right one. Yep. And turn that one off. So we're just only looking at the positive outliers, and this is where they sit in here. All right, so looking at this in this context, it allows you to explain. So remember to always put the context of the geology in front and center, right? So what I would do is, if you do this sort of thing, always try to understand if these real anomalies correspond to something that you would understand geologically. So yeah, a couple of ways to deal with that. And what I've shown you just now is just that regression workflow. But of course, another way that you can deal with this, just divide arsenic over iron to normalize the data to that scavenging effect. So yeah, back to you, Sam.
Okay. Oh, right. Okay. So it's actually almost right back to you, Putra. So I think
Yeah, okay.
just to kind of like change it up for everybody, a lot of times we use multivariate statistics in a way to just be not fancy necessarily, but just to, give information about maybe different lithologies or different alterations or vectoring to mineralization. But Putra has a really fun workflow to which we can use it for data conditioning. So that's what he's going to show to us now.
All right, excellent. Okay, so let's get back to that Flin-Flon data set. And what we're going to do now is I'm going to show you sort of the pitfalls of feeding everything into your data science type tools. So there's a lot that needs to be done before we get up to that stage. And some of those things include data conditioning and understanding where your data comes from. And that's why it's really important to have really good metadata, because it allows you to avoid the mistake that I'm going to do now. So if we're looking at just a bunch of variables, so I got a few shortcuts in here just so we can speed things up a bit. But I got a few elements in here that I used to show for this webinar, and that is by running things on a PCA. So if you ever run something like a PCA or k-means clustering or something like a UMAP, so a lot of those multivariate statistics tool, those tools rely on understanding that your data has multiple populations in it, and there are variants in the columns that you select that can be summarized through something like PCA, where if you look at something like PCA, right, it's where the principal components basically describe components that describe most of the variability in the data. And something like k-means clustering and UMAP try to understand the structure within the data. And a lot of those things are conditional on existing structure within the data, but not all existing structure in the data are related to geological process. So some of the structures that we see here are related to differences in detection limit, and that shows up in your split probability plot. And if you look at the split probability plot, you can kind of see what we're dealing with. So it's almost like a preview of what we're going to be facing. So if you plot all of these ones and say, if you don't have this knowledge, if you approach it like this, right, you don't know the assay method, if you don't have that metadata or you choose to ignore it, if you plot it in something like PCA, I'm going to plot a PCA by plot, this is what you see, right? So you see two clusters, and you can erroneously say that, this cluster at the top, if you look at the eigenvector arrows in here, this cluster are higher in things like silver, antimony, bismuth, tin, tungsten. So all of those good things that relates to Pathfinder elements, right? But once you look at why that's the case, and actually these are higher in these elements, especially if you plot things like, so it's not entirely wrong, right? So if you plot something like these two elements, with these two eigenvector arrows in here, and if you plot, this my bismuth. So if I plot bismuth against tin right here, right? So pretty horrible data. I should probably show this later, but pretty horrible data, but still pretty high, pretty strong positive correlation. It's not that it's not a strong positive correlation, but there is, especially if you transform the axis, but it's just poor quality data, right? But it shows up in the PCA, and this is what happens. And if you now color things up by sample method, some of you might have already guessed that this is what we see, but this is exactly what we're seeing. So the fact that these two clusters are different to each other is a function of the difference in the detection limit. So if you level your data, yes, maybe you can get around that. You can sort of get around this problem. I would be very careful though. You got to know exactly why you're doing it. But I would just omit some of these elements which have a vastly different detection limit, right? Because this is what it looks like in something like PCA. So another fun example, let's remove the colors again, and let's plot something like my favorite new tool in ioGAS, which we introduced a couple of releases ago, and that's a UMAP. So a UMAP is a nonlinear sort of dimension reduction technique, and it's different to PCA. It has more similarities to something like k-means clustering, but if you look at the clusters in the UMAP, you see, oh, fancy, you got several clusters in here, right? And there's the variable plot behind this window that tells you what each cluster sort of represents. So this cluster is higher in certain elements compared to all the other clusters. And guess what? When we plot up the sample method, the differences are actually due to the difference in the different analytical methods. So this is one of my favorite things to show why you need to take metadata into account when you look at your data, because some of the differences, and it affects two things. It affects how you interpret it, but it also affects your choice of elements to include in a data science type technique. So I'll just leave it at that and let Sam finish up.
You want to move it to the next slide?
Yep.
Yeah, so just some closing remarks. Just you got to be cautious always with these, whether you're using a math approach or you're just looking at data for the very first time, like I was today, and it was horrific. Variations in chemistry data are a function of multiple things, not are all necessarily related to geology. Standardized sampling and analytical methods. Look, it's not always going to be realistic because like the whole purpose of the seminar is that we inherit legacy data sets and we work with what we got. Going forward, do the best that you can do. So if you're using drill core data, you want to be doing a 4-acid ICP-MS or ICP if it's in a mine, like at minimum, right? So collecting the best data that you can from the get-go is always going to be best. But you just have to follow the rules of best practice, right? But also, and that just speaks to also minimizing variability going forward in your sample collection, your analytical process, and just having good spatial context on where all your samples are and the different analytical methods that you've used. Sometimes, look, a lot of times I saw a question of leveling in our chat over here. A lot of times, look, when looking at a new data set or an existing data set, many times I'll be in a place where it's just like, okay, look, I have 3 different analytical packages in here, and the way it actually makes the most sense to interpret this is to do it one at a time, based on the results of my best case scenario, and then try and hope that trickles down into the lesser preferred methods. So just every data set's going to be different, and you just have to let it guide you in how you sample, which is maybe a cop out to say, but it's unfortunately what we got. Yeah. So, but at the same time, geochemical data is geological in nature. It is spatial. So just keeping that in mind as well while interpreting it is really going to serve you. Next slide. Oh, and thank you guys. Putra, do you have anything else to say?
Not so much, but let me just go back to the previous slide, because this is a really good sort of summary of where we landed. But as Sam said, just in her last sort of sentence, what we're looking at in assay data is we're not just looking at a table of numbers. Despite the temptation to deal with it as a table of numbers, it really isn't. So you have to understand that it represents a sort of signal that you get from processing your data, right? So when we look at assay data, then it becomes a bit trickier, because when you're dealing with different completeness of the digest and things like that, and different methods, and especially with how little of a sample that gets put into the machine, you have to really understand homogenization and how representative the sample is relative to what you're looking at in the core. And if you look at a big picture kind of things, what's sort of the right amount of sample that can be used to represent the geology of what you're dealing with, what is fit for purpose in your data. And that's why orientation survey at the start is really good approach to start off your project with, just knowing what works with your project and that sort of thing. So yeah, I'll just leave it at that.
Yeah, awesome. I guess you mentioned a little bit about labs in there. Not necessarily a shameless plug, but I've been doing on my consulting company's website, I've been doing a blog series the past month and a bit on geochemical labs, like everything from submitting through to digest analysis, and if that's going to be something helpful just to refer back to as well. But yeah, we're all about trying to unravel the mysteries that is geochemistry. There's
That's it.
also a Geochemistry episode just out. Was it this month, Putra? Yeah, just out this month.
Yeah, it was last week.
With Putra last week.
Yep.
If you guys want to listen to that, where we talk more about historic data sets. And yeah, if you have any questions, we had some in the chat here, but it's 5, or rather the hour's up, so I want to let everybody go. But any questions otherwise that you have, you can send either of us a message. And thank you so much for coming.
Thanks. Thank you, everyone.